So this is the Boston housing data set. So the case study that we have is on Boston housing. So we have the different features of a particular district in Boston. And based on that, we are trying to predict uh, what is the price of a particular district in Boston. So that's the data set. This is what we have in terms of the data set. So if you want to get a little clarity, you can Google out. It's a very popular data set. And we are not loading the data from any CSV file here. We are taking a tf.keras.datasets. You can see it's a default data set that is built into, it's actually built into Keras. If you want to know about this data set a bit more in detail, you can go to Kaggle, you can look it up. You can look it up, you can see the data set, you can understand the features. Let me show you, let me show all of you. This is my data set, all of you. The Boston housing data set. Don't have to memorize, okay? So all that we are trying to do, we are looking at the different features of a particular district in Boston. And based on that, we are trying to predict what is the median housing value of a home in Boston. So the last column is the output column. There are total 14 features you can see, right? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 input features. And based on 13 input features, we are trying to predict what is the output price. It's a simple housing price prediction problem that we are trying to solve. So what could be a practical utility for this exercise? What could be a practical use case for this? Well, maybe you can think of it in the context of a real estate company. You have a real estate company who which is trying to estimate prices of houses in different localities. So they're looking at different patterns, like here you can see the features like what is the population, what is the pollution levels, how far is it from the city center, how far is it from the river, right? So is it near to a port, things like that. So uh, you can see this also looking at nitrogen oxides concentration. So that is giving an example idea of the pollution levels in the locality, right? So weighted distance to 5 Boston employment centers. So if you're very close to an employment center, most likely your prices are more. But if you're very far away, maybe if you're in the outskirts or the suburbs of the city, then the housing prices are much lower. So these are the features that we are using to predict the prices of the houses. So moving on, let me run the code, and I'll be doing the demo. First one, at least I'll show you how it's working out. So this is straightforward. We are running this in Colab, all of you can see. And so first thing, we will load our data. The first thing, we load our data here. And this is my data frame. And we do some normalization. This is done for scaling because my data is in very, very different scales. This is just an initial bit of scaling I did. And what I really want to do is come to this part. This is the most important part where we are actually building a graph in Keras. This is the most important piece of code. Okay, so first time we are actually seeing a particular graph that we are building using TensorFlow Keras. So what is going on? What is going on behind the scenes? What is the meaning of this code? So first, we are instantiating a sequential model. So what is a sequential model? A sequential model is one where you have a very clearly defined sequence of steps. You have a very clearly defined sequence of steps. The output of the initial step, the previous step, will become the input to the next step. So that is how we define a sequential model. You can create different types of models in Keras. You don't have to do it in sequential. But the moment you say tf.keras.sequential, that means whatever you do, whatever you add, let's say you say model.add, model.add. So all of these are getting sequentially added. Imagine it's like it's like a kind of a stack. You're creating a stack. So first you add this layer, then you add this layer, then you add this layer. So you're stacking multiple layers. This is what we call a sequential model, right? So the very baseline model that we are creating consists of 13 input features. Okay, so we have x1, we have x2, we have x3, and we go all the way to x13. Okay, so we have 13 input features, x1, x2, x3, up to x13. So these are the 13 input features we have. And based on the 13 input features, we want to predict what is the price of the house or the median, median prices of owner-occupied homes. This is the neural network we are trying to create, neuron we are trying to create. Okay, it's a price prediction that we are trying to do. So based on the input x's, we are trying to predict the output y. And that's the network for you. You can see first we have got input 13 comma. 13 comma means there are 13 features, and that's the input layer. So we are reshaping that. And then output is dense of 1. What is the meaning of dense of 1, friends? Dense layer means a fully connected layer. So what is a dense layer? A dense layer means a fully connected layer. That means uh, that means the neuron is connected to all the previous layer neurons. That is what we call a dense layer, right? So dense layer in this case means this neuron, whatever neuron you are seeing right now, this neuron is connected to all the previous layer neurons. So the output neuron price, the output neuron right now is price. So this output neuron price is connected to all the input layer neurons. That is what we call a dense layer. But otherwise, there is why is it one? Because we can understand there is a single output. We only have a single output here, so hence it's a single neuron that we are trying to predict as the output. So once that is done, now this is the architecture that we designed, and now we can define our loss function. Okay, so that's the easiest part. So we can go and define the loss function. So loss function we can give a default loss function, and the loss is MSE. Okay, so we can run this part, and we can also see the model summary. And the model summary is exactly what I explained. You can see there are 13 inputs and there is one output. And you can also see that there are total 14 parameters. Why are there 14 parameters, friends? There are 14 parameters because there are, what are you primarily trying to learn? You are trying to learn 13 weights, W1, W2, W3 up to W13, and one bias. So total there are 14 parameters that you're trying to learn. Okay, so how many total parameters are you trying to train in the network? There are total 14 parameters that you are trying to train. So there is some X, there is some Y, and overall you are trying to learn 14 parameters. The 14 parameters that you are trying to learn. 14 weights and biases you're trying to learn in the network. Okay, that's the idea. So obviously you can understand the deeper the architecture. If I add some hidden layers, which I will add shortly, if you add hidden layers, then you will have more number of parameters, more number of weights and biases. Okay, and this is the math. This is the maths that is working out behind the scenes. You can see 14 parameters we are trying to learn. And weights and biases are what? What are weights and biases? This is actually float 32, right? The TensorFlow default is float 32. Okay, float 32 means what? 32 bits, right? 32 bits means 1 byte. That means every number, you're like storing 4 bytes. 4 bytes means 32 bits, right? So each number is 4 bytes. So 14 numbers, 14 fours are 56, 56 bytes. This is the amount of space you need to store those 14 parameters that you trained. This is a very, very simple architecture we are seeing. It's a very simple neuron where there are only 14 weights and biases that you're trying to tune. That means at the end of the neural network training, right? And you can see it. Let me just show the training also to all of you. At the end of the trainings, I can just go and run this model.fit for 100 epochs. And when I do that, you can see it's trying to train and it's trying to learn the weights and biases. Every iteration, you can see the loss is reducing, loss is reducing. And at the end of it all, I will get these weights. At the end of 100 epochs, I would have learned the weights and biases. And this is what you're ultimately saving. So when we say in deep learning that we train the model, a model is nothing but its weights and biases. So two things. One is the architecture. What is the architecture? Architecture is 13 and 1, whatever architecture we define, the summary. And what are the weights and bias numbers? Okay, so that part is also very, very important. Then we can save the model. Then we can save the model. We can deploy the model. Okay, so this is broadly what's going on. So this part is very important to keep in mind because, like if you have a very deep architecture, like here also, if I add some more hidden layers, and which I will do now, because very clearly you can see the loss is pretty high. Like even after we train for 100 epochs, the loss remains 400. Loss seems to be very high. Okay, so now what I will do, I will go back to the dense layer, this part, and I will simply add 2 additional dense layers. I will simply add 2 additional dense layers. So what will happen here is I have to run again from here. You can look at the model summary. It's a lot more complicated. Can you see? because I added these additional hidden layers, I have more neurons that I've added here in between, and that's why the overall number of parameters is 2421. And the total size that this will take to get stored is how much size we will need to store this. The total size, the total size that is needed to store this thing is 9.46 KB. So we need 9.46 kilobytes to store this entire thing. Okay, so all of you are able to get a sense of this. And you see, that's why even today, like all these large language models that we see, like GPT and Gemini, we have all these large language models that are available. In all these large language models, also like what we see, you'll typically see that they are huge language models. Several millions, hundreds of millions to billions, to several hundreds of billions to trillions of parameters. In fact, today's large language models have upwards of trillions of parameters. So what is that parameter? When you see a LLM, when you see a GPT model, a Gemini model, what is it? What is it behind the scenes? Behind the scenes, it is a neural network. It is a neural network that is trained with lots and lots of data. And behind the scenes, companies like OpenAI, companies like Google, companies like Meta, they would have used a lot of computational resources. Neural networks would have been used to train the networks. And at the end of the process, you would have learned the weights and biases. Ultimately, you're trying to learn. So next time you read an article and it says, hey, you know what? We have the Gemini model with a trillion parameters. You know what it is. You know that there are trillion weights and biases. And that's why these models are massive. A trillion parameters, you can imagine. You do the maths right now. Even if you, like, there are other efficient ways they do the computation. You do the maths. You take, like, this is what, 2421 into 4, right? It is taking this much kilobyte. You take 1 trillion. What is 1 trillion into 4? 4 trillion bytes. That means 4 trillion bytes. Now you do the maths right now. 4 trillion bytes means how we can even save those kinds of things. And there are different efficient ways how they do it. That's another different conversation altogether. But the idea is to educate you and tell you what is the meaning of a model parameter. When we train a deep learning model, what exactly is a model parameter? Model parameters are the weights and biases. And that is exactly what you're learning. That is exactly what you're training. When you do gradient descent, you're updating those weights and biases. And at the end of all the epochs, this is the final thing that you're trying to get. And to save it, you need space. You need memory. Okay, that's why these are very, very memory intensive applications. So let's see that after we add these two hidden layers, did my network improve? Did my loss drop? My loss was seemingly very high initially. Yes, surprisingly, it's gone better. No, remember, initially after 100 epochs, my loss was what? It was around 300, right? Can you see? Surprisingly, my loss has dropped. That's the magic of deep learning. It's not guaranteed that if you add 100 layers, your loss will be zero. It's not guaranteed. This is again a trial by error process. You will have to iterate. You will have to. It's just like a hyperparameter. You have to try different approaches, and you have to see that with which approach you are getting the best fit model. So the conversations about overfitting, underfitting, all that holds true. All the overfitting, underfitting ideas that we covered, all that holds true, right? If you have too many hidden layers, what will happen? The network will overfit. Okay, if you have too many hidden layers, if you have too many hidden neurons, what will happen? You will have overfitting. And if you do not have too many hidden layers, what will happen? You will have underfitting. So overfitting, underfitting, all those are related ideas that we have here also. So too many hidden layers, overfitting, and if you do not have too many hidden layers, it will be underfitting. So if you get the weights, let me see what the weights. Lot many weights are there. You can see very clearly. There are 2,421 weights and many weights and biases are there. So these are the numbers that we actually learned in the process. If you want to train it more, if you think that, okay, there's a scope to make it more, there's a scope to reduce the loss even further, you can try it out. Now, these are the experimentations that you can keep doing. Okay. Now you can maybe take another dense layer. You can probably take 1,000. We can maybe start with, or maybe not 1,000 will be too much. Maybe we can take 200. And maybe I can add another dense layer. I'm trying to really complicate the network right now. You can see. So dense 200, dense 100, dense 50. And this is generally a preferred way of doing it. You start with lots of features and you try to narrow down. It's generally a best practice. So now let me try this architecture. So naturally, you can see it's a deeper architecture. There are 28,000 parameters. It's a much deeper architecture with 28,000 weights and biases that we are trying to train. And if we go and do this, let's see, it will be a little slower comparatively. and it will be interesting to see if it made any meaningful difference to my overall losses. Okay, and you can actually monitor. I think it's probably reduced a little, not a lot, but I think it's reaching the 28 mark, but it's fluctuating. And as we go through the conversations, we will see different callbacks to use, different checkpoints to use, but definitely I am able to touch a 28 loss. If you want to further train it for 200 more epochs, what you can do, so you can just run this code again. Don't have to run from the beginning. You already did until model.fit, just run this again. Okay, just control enter, run this again. And you can see, look at it, I got 24. So definitely, as I train it more and more, I am able to get better results. Look at this, 21, 22. I am seeing things that I did not see before. 18, 16, 14. Incredible. I can train it for, maybe now I get the confidence, train it for 500 more epochs. Let's see. Let's see. If I train it for more and more duration, there is a possibility of my loss reducing more and more and more, because I have a very powerful network. I have a powerful network that is stacked over 4 hidden neurons. And the more I train, the more weights and biases I'm trying to learn. You can see I'm going to single digits now. I think there was a time I saw 9 or 8 come. Okay, so it's fluctuating. See, this is 9, loss of 9. Can you see? Loss of 9 is incredible. We did not have this value before. We are seeing a loss reaching even up to 9. So previously from 500 we come to 9. So this is the demonstration I wanted to show you, how you can train the weights and biases, how you can make it better, and how by iterating over many epochs you can get a very good model. Look at it, I'm even touching 8 now. I'm even touching 8 now. And maybe if you go further over more epochs, you will get even better. Even better. It's not guaranteed. It's not guaranteed that you will always do well. But generally, if you add more layers and if you add more neurons in the learning process, you will get a good model. But you will have to monitor overfitting. Okay, because remember, this is the training loss. So what you're seeing on the screen is a training loss. So there might be a possibility that the training loss is reducing. If you're building a very complex model, your training accuracies are going up. The training loss is reducing, but your validation scores are bad. So you need to add a validation loss also, which we'll do shortly. Okay, so that's something we will do. But yeah, I hope the core ideas are clear. Yeah. Mhm. I will talk about it. For now, activation, just assume there is something we have here. So activation at a high level is this, but what exactly it is going to be my next discussion. I will talk about it. But at a very high level, activation is this. Remember at the beginning, I told you that when you use a neuron, you are doing that sum of products computation, and then you do something else. This activation is an additional mathematical function that you're using. So you take the initial inputs, you multiply with the weights, add a bias, and then you go and you perform another additional mathematical computation. That is what we call an activation. ReLU activation, that's a mathematical part. ReLU activation, what it does behind the scenes is something like this. This is actually mathematically, this is exactly what ReLU does. You can see ReLU stands for rectified linear unit. So this is one of the best activation functions that we use. You got it right. This is the math behind ReLU. Yeah, there are a lot of activation functions in deep learning, and at a very high level, activation functions are used to introduce non-linearity in the network. Okay, because that's the whole objective of deep learning, right? I'm not getting into the mathematical explanations and theory and all that. That's an entirely different conversation. But at a very high level, activation functions are used to introduce non-linearity. Just remember, in a neural network setup, activation is a default feature. So whenever you are using any neural network, the hidden layers, you will by default use something called a ReLU activation, which means again, at every neuron, you are doing this computation and you are performing an additional computation with an activation. This is the ReLU activation you're doing.